Hi. So, this is going to be our last video, and here I'm going to explain to you how the customer maximizes his or her utility. Okay, so this is the problem we've got. Look, we've got a utility function. So, utility here is a function of quantity of good x and quantity of good y. And now, customer has a budget P. Here are the prices of good X and Y respectively, and X and Y, of course, denote their quantities. So how do we deal with this? First, we build the Lagrange function. So we got Z, the original utility function, plus lambda, we open brackets, B minus Px times X minus Py times Y. And then we get to first order condition. First, we differentiate z with respect to lambda, x, and y. After differentiating with respect to lambda, we get simply the repetition of a budget constraint, right? Differentiating with respect to x, we get that this is marginal utility, derivative of this part with respect to x minus lambda. Out of this we get negative px times lambda, negative lambda px. This equals to 0, and as you see, out of this we can calculate that lambda is equal marginal utility of x divided by price of x. And finally, we do the same thing but now we differentiate with respect to y. We get marginal utility of good y minus lambda times py. Out of this, we can calculate that lambda is equal to ui over py. Now, because of those two, when we compare them, we get ux over px equals to ui py. Now look, we can divide both sides by ui and multiply by px. Then we will obtain this, and finally, we can multiply both sides by negative 1. And what do we obtain over here? We obtain our optimum condition. And we see that on the left we have negative ux over ui. This is nothing more than the slope of the indifference curve or marginal rate of substitution. Here, on the other hand, we've got the slope of budget constraint. This actually tells us that customer maximizes, his or her utility at the point where budget constraint is tangent to the highest obtainable indifference curve. And look, let's see it on a graph. Look, this is a budget constraint for the budget we've got. And here we have three different indifference curves, right? We see that this one is unavailable to the customer because the customer does not have enough money. This one is available to customer, but we can clearly see that this is not the best option because we can increase the utility. And remember, we increase utility when we move to the northeast. So if we would be moving this indifference curve higher and higher and higher and higher, we would end up at this point. And this point is the customer optimum. At this point, so with this quantity of good x and this quantity of good y, customers' utility will be maximized. Okay, we said this a little bit ad hoc because we still haven't calculated the second order condition. Okay, going back a little bit, in order to obtain second order condition, we need to calculate the Hessian. So we take this system of three derivative equations. So these three partial derivatives, and we differentiate each of them first with respect to lambda, then with respect to x, then with respect to y. We obtain this. After multiplication of all of it, this is what we will get. And look, what do we see over here? Uyy is clearly negative by assumptions. We assumed this at the very beginning. P is price, it's positive. And look, so this is negative, this is positive, it's minus, so this term is positive. And the same with uxx, it's negative, price is positive and it's squared, minus, so this must be 2 minuses, it must be positive. 2 times px, py, definitely positive, but we do not know, and we didn't impose any assumptions on this term. Well, it's definitely gonna be positive if the goods are complements. But actually, we can get a better clue when we differentiate indifference curve for the second time. So look, we are calculating d square y dx square. So we simply differentiate the slope of the indifference curve. Okay, first we need to use the quotient rule. And look, here, in order to calculate it, we can either use the chain rule and total differential. And look, let me explain to you how this works. Look, because ux, remember, is a function of both x and y. So we calculate derivative of ux, a differential of ux. We get that this is dux equals to uxx dx plus uxy dy. We divide both sides by dx, and this is the expression we've got. And look, we do exactly the same thing for dy, duy, dx. Okay, in the next step, we can substitute dy dx with negative px py, because at equilibrium point, negative ux uy is equal to negative px over py. Okay, and finally, we will use this in the last row. We are using the same information again, but look, now out of this negative ux uy negative equals to negative px py, which is equilibrium condition, well, optimum condition, which is a special case of equilibrium. Here you see we can calculate ux, and we substitute it over here. Now if we would now multiply it all out, this is what we would get at the very end. And look, what we have at the top is nothing more than a Hessian. On the bottom, both expressions, squared price, positive, marginal utility of good y, positive. So this expression will be positive as long as Hessian is positive. And look, if this expression is positive, second derivative is positive, it means that the function is convex. And look, this is the most important thing here. The function will be, so we will always have maximum, because then we will always have positive Hessian as long as the indifference curve will be convex, so it will have a shape that we considered. Where this convex shape comes from, in more detail, you will hear from Dr. Nennemann during intermediate microeconomics next semester. Okay, so now let's just do an example. So look, we've got the function u equals yx, b, our budget, equals 100, price of good x is 5, price of good y is 20. Look, now out of those three, we can easily build budget constraint, and then we can build the Lagrange function. We differentiate it with respect to lambda, x, and y. And look, we see here that we have linear functions. We do not have any squares, logarithms, exponential function, nothing like that. just constants and 3 variables with coefficients. So what is the best thing to do? Of course, it's to use matrix algebra. We put this whole thing into a matrix form of a system of simultaneous equations. And remember, in such a case, determinant of matrix of coefficient is equal to border Hessian. We calculated, you see here, I've taken out of the first row and out of the first column -5, so I have 25 up front. After calculation, it's 200, and because it's positive, we know it is a maximum. Now, we take vector of constant terms and we replace the second column because for now we don't need lambda. So I use the same trick. Now I'm taking from the first column and first row. From the first column, I'm gonna take -5. From the first row, -20. I get 100 up front, and now I'm taking 5 out of the second column and 4 out of the third row. It's 2000. After calculation, it's 2000, and we get that customer maximizes his or her utility if he purchases and consumes 10 units of good X. Then, in order to obtain good Y, value of good Y, we first calculate AY. Now we replace third column with vector of constant terms, and we do use the same tricks. Out of the first column, I'm going to take -5. Out of here, -5. 25 is up front. I can also take 20 out of the last column. I've got 500 up front. After calculation, it's 500. And we see that Y is 500 over 200 is 2.5. Look, we clearly see that those values give us here 50 plus 50, so budget constraint is fulfilled. Now, what is the highest utility customer can obtain? Well, we see that we will obtain it simply by multiplying the value of X we obtain by value of Y. So 10 times 25, which gives us 250. Finally, we can put our answer on the graph. We start by drawing a budget constraint. And look, simply we take budget constraint, we solve it for Y, and then we can draw the line. We see that when customer spends all the money on good Y, customer can purchase 5 units, and all the money on good X, 20 units. Now we know that the equilibrium point is at when customer purchases 10 units of good X and 2.5 of good Y over here, and this is the point at which budget constraint is tangent to a highest attainable indifference curve. Okay, so this is it. During workshops, you will be practicing this with Valeria. In the next video, I'm gonna discuss what's going to be on the final exam. Thank you for your attention, and see you in the next video.